Can I start? Well, hello. Today I'm presenting my work, which is entitled An In-Depth Analysis of Implicit and Subtle Hate Speech Messages. It's a work that I will divide in two parts. The first one is something that we work with Katerina. It's on the construction of a benchmark. And then the second part is about the generation of implicit instances that help to improve our results on that benchmark. So before I start, just a content warning. Since throughout my presentation, I will be using some abusive examples in order to explain the different notions. But, well, by no means they intend to offend anyone. So hate speech, implicitness, and subtlety. I will start explaining what is hate speech. Basically, messages that are considered hate speech are a direct attack against people that can be an individual or a group based on what we call protected characteristics. This can be race, ethnicity, national origin, disability, religious, among others. And from this, we extended this definition to consider different aspects. In this case, explicit hate speech, which is a hateful message where the hateful part contains insults and explicit phrases. Then we have implicit hate speech, where it's similar, but the hateful part, it's coded in what we call implicit devices, such as sarcasm, irony, exaggeration. And then we have subtle hate speech, which can be either implicit or explicit. Basically, here we don't focus on the hateful part, but what happened around. In this case, what happened around can deviate the focus on the hateful part. So just for you to understand well, I will show some examples of this. Imagine that this is a set diagram of hate speech, and with the definitions we already said, we divided in four this diagram set. So the first notion, explicit and non-subtle. This measure is it's clear, it's direct, it's hate speech, and also we can clearly identify the hateful expressions. Then explicit and subtle. Here, the third highlighted part, it's the explicit expression that we are considering here. And then the first two construction is the subtle part, basically add more weight to the sentence and deviate the focus of the third one. Then we have implicit and non-subtle. Here, we don't have constructions as we had in example 2, but the whole sentence is ironic and with a bit of black humor. And then we have implicit and subtle, where the highlighted part is the construction that deviates the focus of what comes after. So, well, in order to understand the different, how to tackle hate speech detection, first we have to know what are the studies which are currently now. So, well, among these studies, we can find supervised methods to classify only explicit hate speech together with the annotated datasets. Also, there are some datasets for classifying implicit cases, but the problem is that they are constructed based on filtering techniques and they are biased. Also, none of the previous work considers subtle as a separate concept. Another problem is that most of the datasets are collected from only one source. In hate speech, well, this is important because you normally don't want a dataset that only tackles 2 pieces, 3 pieces. You want variety there. And also, those cases that tackle implicit, they don't go further and they don't analyze fine-grained annotations or notions. So, well, in order to tackle more or less these issues, we decided to focus on creating a new dataset. We call it IS-Hate for implicit and subtle. Basically, we built it using 7 resources, which were already annotated with hate speech and non-hate speech labels. But the main difference is that we didn't consider those resources that were biased. I mean, we tried to focus on resources that were collected on based on hateful users. So, well, we divided in 4 layers. The first layer is this one, the hate speech and non-hate speech. Then on top of hate speech, we added 2 additional more, which is the implicit and subtle ones. And then on top of implicit, we added the what we call the implicit properties. So for an implicit message, we had to justify which were the devices that code the hateful meaning. And well, this is some of the distributions of the dataset. For example, here for the non-hate speech and explicit and implicit, and we can see that we have an imbalance for the implicit class, and it happens the same for the subtle one. So this is a problem that we will be tackling just in a minute. So these are the implicit properties. There are a total of 18, and here, well, with the help of Ekaterina, we perform a pilot annotations on this dataset in order to try to identify which were the most significant properties that in which the messages were encoded. This is a distribution of these properties, and well, we can see, for example, here that the most significant ones are inference, context, sentiment, exaggeration, and irony. And among the resources, just to mention them, well, one of them is it's from a white supremacy forum dataset. Then we also have Hateval, which is a dataset very well known in the community of NLP and in the area of hate speech. Then a dataset oriented to implicit detection, the implicit hate corpus, it's a very new one. Then Toxigen, which is a dataset which was machine generated, and it was we also consider worthy to include it. A dataset constructed based on YouTube video comments, videos that were, let's say, controversial. And then Conan and multi-Conan. Basically, these two datasets are pairs of a counter-narrative and a hateful message and a counter-narrative. And we thought that it might be worthy to include it too, because since we are providing a counter-narrative, a hateful message, we expect that this hateful message are rich in content. So this is just a snapshot of how it looks like, the dataset. We have a column for the text, then the source, and the 4 layers: the hateful one, the implicit, the subtle, and the properties. So now, in order to tackle the problem of the imbalance, we try to perform some documentation on the training set. Then the development and test, they were kept untouched in order to respect the real distribution. So but for the training one, we apply some techniques. So now I'm going to describe each of them. The first one is replace name entities. So basically, we took an input message and we identify entities like pair, lock, organ, misc. And then we replace one of these, a candidate entity, for another one, which was the most similar, right? So here, as we have in the example, the entity Muslim, and then we replace it by the most similar one from a previously collected list of entities. Then another one is to replace scalar adverbs. Basically, we identify an adverb, which is a scalar that is, an intensifier of a verb. For example, so, and then we replace it by another one, which is similar. Then add adverbs to verbs. This is also pretty straightforward. We have a verb, for example, here in the original sentence, the verb to be. And then we modify it by adding before and a speculative adverb. With a speculative, I mean it's an adverb that adds some like probability, like possibly, likely, clearly. Then we have replace adjectives. This is again very simple. We just replace another adjective by their synonyms, like we see here in the original and the augmented sentence. Then replacing dominant expressions. We created a manually crafted expressions from the dataset, and we tried to capture some replacements that weren't done by the other ones. So, for example, the name entities, and in order to have some other replacements and more variety. So in this case, we took, for example, migrants, which wasn't captured by the name entities. We apply some other replacements. Then you see the documentation. It's a very interesting one. It applies 4 operations. One of them is random replacement, insertion, random swap, and random deletion. So here another example, we have this order, and then it swaps the words in order to have an augmented word. And then we have a back translation. It's also very straightforward. We take an input message and we translate it to another language, in this case, Russian, following a previous work. And then from Russian to English, we translate it back. So this is the original and the augmented one, and the changes, well, we can see it here. So they are very like cosmetic changes. And also we experimented a bit with generative models, trying to fine-tune a model on the minority classes, with examples of the minority classes. And then we were expecting to obtain some augmented sentences from them. So well, this is another example from these generative models. Then we will go deep on generative models, but this is just a preliminary approach. So these are the number of additional instances. Take into account that, well, some of these strategies might generate more messages than others. So for example, if we are replacing adjectives, but in the input message, there are no adjectives, well, we cannot generate a new one. But if we have another case that has a lot of adjectives, well, it might generate more. So, well, for example, here, RSA, AAB, IDA are the most generative ones. And then BT, for example, we have a limit there, which is the number of instances we have in the minority classes. And this is the redistribution for, after applying the augmentation. So the column ORIC, it's the original distribution, and then the other columns, the augmented ones. So, well, just to mention a few, again, the most generative ones manage to balance the data sets. But, well, in the case of BT, for example, we cannot like perfectly balance the labels. So what? Now we proceeded with the evaluation. We try to evaluate state-of-the-art models on this new benchmark. Basically, with state-of-the-art, I mean the first-rank models of the resources that we collected. And these are, well, the universal sentence encoder plus a supervector machine, BERT, HitBERT, and DeBerta. And we propose the task, a 2-3-level classification task. Task A, we define it, in order to classify messages on non-hate speech, explicit and implicit, and non-hate speech, non-subtle and subtle. So, well, these are the results of the first task with augmentation. So, well, we can see that the model behaves well to detect non-hate speech and explicit, but then we have well, limitations to predict implicit. But still, we are better than random guessing. Remember that if you are in a 3-level classification, the random classifier is 0.3. Mm-hmm. Well, then, after applying augmentation, we could see that we could get an increasement in implicit detection, in implicit class, without neglecting the other labels. Just to mention another few interesting cases, for example, BT, that doesn't have a lot of messages, it still managed to have very good results on implicit. Whereas in the case of the most generative augmentation strategies, didn't behave well in the end. And then for generative models, it was a bit strange in this case. So for example, here for GM, it's for the generative cases using the fine-tuned models, but still we couldn't get enough results, and even after apply some revision to these cases. So the winner in this case was HitBERT plus Hall, and these are the most misclassified implicit properties. So we took this model and we applied some error analysis. So well, we can see that the most misclassified properties were inference, context, sentiment, exaggeration, and extra-linguistic knowledge. So at first test B, these are the results without augmentation. In this case, we had a worst performance on the subtle class without augmentation. But then as soon as we start adding more instances, we could see some improvement on the subtle class for HitBERT plus Hall. Also with back translation. In this case, we got some good improvements using the generative model approaches RNI, and also with the generative models. But well, the winner was the supervised machines plus the back translation. So well, after applying some error analysis, we could see that most of the misclassified examples were because of word order and circumlocution. So well, we also tried to plot the different embeddings of these models. So we have in the image above, we have the model of the task A. So we can see that it manages to separate well the blobs of non-hate speech and explicit, but as soon as we go to implicit, there are some points which are spread on the other two blobs. Whereas in the case of the supervised machines was a bit strange. Here the embedding is the universal sentence encoder. And well, I have some hypotheses regarding the results we saw in the previous table. So, well, one possibility is that the t-SNE, which is an approximation of the embeddings, probably in a higher space, they might look more separable. And also, well, since supervised machines is a nonlinear model, it managed to find some separation even in this space. So what? So we can see that obtaining generated data from real messages play an important role in the system performances. However, we just experimented with simple generation strategies. So in order to go farther on this, we tried to experiment with adversarial implicit instances. And in particular, we wanted to go with language models, with generative language models. But this time, instead of fine-tuning on the decoding part of the generation, relying on 4 components. One is, well, prompting, in this case, demonstration-based prompt, which is a subtype of prompting, a search method, a call function, and a set of constraints, which I will explain a bit later. But just to make sure that we're on the same page and that we all understand what is adversarial, I have a slide dedicated to this. Basically, adversarial examples is an input designed to fool a machine learning model, and they can be helpful to grow wisdom over handling models misclassification. And in particular, we look for improving classification results on the benchmark. We also try to solve this data disproportion, trying to propose some large collecting methods. We want to find a text variety for training instead of only applying some replacements. And also we want to reduce cost on obtaining implicit and subtle messages, because as you imagine, this notion requires some knowledge from the annotators in order to make them well. So now I will proceed with the steps of the components I mentioned before. The first one is demonstration-based prompts, the first component. So basically, DBPs are just text fragments passed as input. So this input will help the generator to have some context of the task. And it's called demonstration-based because you inject in the input some example statements. So this is just an example. The prompt is the red and the blue part, and it's divided in the instruction. So the instruction is, I will read it. These are some examples against migrants. Write one more alike example. So this is the instruction I want the generation to perform. And you also, in order to guide the generation, you provide some shots which are, well, implicit instances against migrants. And so then you get the output, which is similar to the shots you provided. Well, if you try this on GPT-2, let's say, you might get some implicit instances, but there's no guarantee that these messages will be challenging for a classifier. So in order to have this property, we applied some restriction to the decoding part of the generator. So we had to do something on the generator in order to make challenging messages. So well, something we provide is a constraint beam search. So I'm going to explain a bit how it is the classical beam search, and then I will add the additional constraints. So given a language model, L, a classifier C, a context, a sequence of tokens, W0 to WI, and a candidate next word W, the generator, what it estimates is the probability of the next word given the context, right? So the generator will apply this, will calculate this for all the words in the vocabulary. And of course, the higher the probability is, the better for W. And then at each step, the generator will select one word using certain decoding strategies. One possibility is top K, so you select the top K scored words, and then you pick one randomly from there, or top P, which is kind of similar. And also you have beam search. I mean, you can apply, you can do the decoding a certain number of times. That's the number of beams. So it's like running in parallel the decoding a certain number of times. So well, this is the vanilla beam search, and I will apply some constraints on this formula. The first one is, in order to challenge the classifier, we want to, what we do is to take the generated sentence, so I mean the context plus the initial word, and we ask the classifier to calculate the probability to belong to the implicit class. And then we make the operation 1 minus that probability, because that will mean that it's the probability of being either non-hateful or explicit. So the higher this probability, it means that it's more challenging. Then we also, we consider a lexicon. So we try to weight the next word, this possible next word, with an implicit score. So for you to know, a lexicon is just a list of words weighted with some criteria. And so, well, this function basically assigns or returns the score of the lexicon if W belongs to the lexicon, right? And then the other constraint is we want to make sure that the output is similar to the shots we provided. So basically, we take here a model of sentence similarity, and for each of the shots, we embed with this embedding. We take the average of these shots, and we compare it with the embedding of the output, and we take the sentence similarity. So that's another restriction. And well, these are all the set of constraints, but now we need a way to mix all the different expressions in one formula, because this is what we want to optimize. So well, one possibility is to apply the multiplication. However, in some cases, you would like to have, I don't know, some more importance to one constraint than another one. So what we did is what happened if we take the logarithm of the whole expression? So when you have a logarithm of a multiplication, it's the sum of the logarithms. So this. And now that we have a sum of terms, we can apply, we can put a hyperparameter to weight each of the terms. So this is the formula we want to optimize, and this will be the constraint beam search. And now on this formula, we can apply the same decoding, that is top K and non-beams. And then for the other two components, the goal function, basically we take an input message, and we need some way to say that the message is challenging. So since a classifier should return 3 probabilities, one for non-hate speech, explicit and implicit, we thought that the expression of the constraint number 2 may be ideal for the metric, for the goal function, because basically the higher the probability of being either non-hateful or explicit, the more challenging the message could be. And then for some constraints, we also apply some automatic filtering to discard generated messages, which are incomplete, short messages that have non-ASCII characters. So now let's go with the research questions. First, we wanted to know if we can generate implicit messages using shots that attack only one specific target. Then the 2 is that, well, maybe we can remove the target and have shots that attack several targets. You know? Then we also want to see how each of the restrictions perform. And also we saw that there is we also have the instruction of the prompt. What happens if we change it? So well, we also want to try to see if there is an impact on the results on this. And also the research question 5 is to find if there is an optimal number of shots in order to have good generations. So now the experimental settings for this part, we have for the generator, we use GPT-3, in particular the version text query, which is the second version of the GPT-3 after the DaVinci. For the classifier, we took the best performance model on our benchmark, which is HateBird. For the lexicon, we took we basically took our benchmark and we weighted the vocabulary, so we'll see it in a minute. And for the sentence similarity, we took the most well-known model for sentence for this task, which is in sentence transformers. So now for the lexicon, something we did is to use point-wise estimation, the PMI, and this metric, what it does is to measure basically the frequency of a word to appear in a document. So here we calculate the PMI of a word W in terms of the document implicit and explicit. So the difference of this will be the implicit score. So we'll get some score on this, and also we applied a sigmoid function in order to scale it in our required range. The problem of this is that since in the constraints, in the formula, we were dealing with probabilities. The probabilities have a range of between 0 and 1. Well, we wanted to have restrictions that are in the same range. So that's why we applied the sigmoid function. So we can see that the least ranked words are derogatory, basically explicit, and the most rated tokens are neutral. Let's say they can start, I don't know, probably an implicit message. So that's why we wanted to go in this direction. So now in order to answer these questions, the research questions, what we did is to first group messages directed towards the most attacked targets in our benchmark. These were Muslims, migrants, Jews, Black people, women, white people, and Asians. And also, we randomly select some demonstration shots from these categories and generate a total of 20 instances per target group, obtaining, since we have 7 categories, 140 messages using GPT without any constraints. Because at the beginning, you just wanted to test if we can use only one target to generate good messages. And then we repeat the same procedure, but without grouping per targets. To answer the research question 3, we carry out just an ablation study throughout all the restrictions. For research question 4, we repeat the experiment of the research question 3, but with different instructions. So one of the instructions we use is, these are some examples against the target, and write one more similar example. Another instruction, we use just a label and the target. So implicit hate speech against the target. And then another case without any instruction. And for the last research question, we just varied the number of shots using the best performing model from the other research questions. So here we can see on red the results regarding for the research question 1 and 2. So when we use MPG, which is multiple target types, we have that it can generate, I mean, among the batch of 140, only 70% of the generation is implicit. So in the end, it seems that it's not a very good approach to use multiple targets. But then once we go focusing on only one specific target, we can see that there is an increment on the number of generated implicit instances, which also keep the target, which is very important. And then adding the different constraints, we saw that, for example, the one that behaves well is the one that has all the constraints. In this case, we could have a similar number of implicit instances as the as the without constraints. We also managed to keep the average similarity between the output and the shots. A good number of generated outputs that keep the target, and also the number of hard cases increase in comparison to the rest. So this is the generation results just for using the instruction 1. I'm not going to show for the instruction 2 and 3 because they were basically the same. In summary, they didn't change. I mean, changing the instruction doesn't affect the results. Then for the number of shots, well, we first saw that there is a rapid improvement if we increment from 1 to 10 number of shots. But then once we go further, for example, using 20, 30, 40, or 50, there is no improvement on the number of implicit messages we can find. Well, now that we have this framework on generation, we wanted to use it in order to improve our hate speech classifiers. So in this way, we wanted to, we implemented a variant of a build it, break it, fix it approach. So what do I mean with this? A build it phase is when you have a machine learning classifier and you train it on a specific benchmark. So well, this benchmark defines a task and you train a model on that task. Then the breaking phase, you use adversarial examples in order to break this model. So in our case, we'll be using the generator that breaks the model with certain parameters in order to attack M0. Then the fix it phase, you take these adversarial examples and you retrain your model on this. And then the repeat phase could be, well, doing this iteratively in order to obtain a fixed model M1, a fixed model M2, and so on. So well, the goal of this experiment is to improve the classification of results without affecting also the performance of the negative classes, right? So well, in this case, we just perform this approach on 3 rounds with a total of 870 adversarial instances, all of them human validated. So after generation, we validate them. And also we make sure that all of them were adversarial, that is, were scored as hard by the gold function. And since we were retraining, so we need instances from the 3 labels. In order to have some negative data, we pick randomly some safe and explicit instances. So these are the results after the 3 iterations. So well, we can see that in iteration M1 and M2, we have an improvement on the F1, but then in the 3rd iteration, we have a decreasement. So if we go on the precision and recall, something we notice is that it started paying more attention to recall than precision. And it makes sense because what is doing the breaker, let's say the adversarial instances, are producing examples which are harder to detect. So well, now when you retrain the model, you will start paying more attention to say, okay, this message that I newly get is implicit. So you will start paying more attention to recall. So that's well, that's one of the hypotheses. I see that there is this change of the metrics. But well, some good thing is that there are no changes on the other labels. So well, in conclusion, we have presented a benchmark, a challenging benchmark to detect implicit and subtle notions, and we also presented a framework for generating implicit instances. And well, we could conclude that state-of-the-art models still fail to detect properly implicit and subtle messages, well, due to these peculiarities, as we saw, connected to implicit properties like sentiment, inference, context, and irony. And also in the case of subtle, as because of complex syntactic structures. Well, we also could see that documentation might play a role in improving the model's performances. In our framework, we also saw that we can produce from a batch of generated messages, 70% of them will be implicit, and also 90% of them will be hard cases, will be adversarial ones. And incrementally retraining with this instances might help to improve even more the classification performances. Now, some limitations in the whole work. Well, we have this intrinsic difficulty to provide some clear definitions. It's something that it took a lot to discuss. Well, within what is implicit, what is subtle, something that we had to agree with. And also, well, the future annotators, let's say if someone wants to take this work and improve the benchmark, well, we'll need to have the same expertise in computational linguistics in order to, well, have the same skill to annotate implicit and subtle messages. And also, well, for the generation part, in order to obtain the results, you still have some way to validate them. And in this case, we couldn't find another optimal way than just doing manual validation. So this is another limitation that of this work. And the last one is that now there's a lot of focus on trying to debias language models. So future versions will be more debiased in order, to produce more safe content. So since the generators, the approach we are using take the most of the bias of these language models. For example, GPT-3 is biased to produce this kind of content. Well, then when you give some demonstration props in future versions, you probably won't have any hateful content. So, well, as future work, we plan to explore on a different direction. And we try to embed implicit and subtle statement implications to find better representation spaces. We try to deciphering models for code language and probably use this work on bias mitigation to improve classification results, and probably extend this generation framework to subtlety. So that's it. Thanks for your attention.